Okay, good evening, everybody. And welcome to another session of organic chemistry. Okay, in today's session, we are going to start our discussion on instrumental analysis, which you will find on chapters 12 and 13 of your book. Specifically, we are going to discuss mass spectrometry, infrared spectroscopy, nuclear magnetic resonance spectroscopy. With regard to nuclear magnetic resonance spectroscopy, we are going to discuss two topics. One is proton NMR, and the other is carbon-13 NMR. Now, fortunately, most of you have already watched the webcast or videos of all of this material before you came in today. So what we are going to do today is essentially go over our problems, do a lot of problem solving. We are going to start with the problem solving, going over the quiz that you guys have just taken, go over those problems, and then if we have additional time, we will go over some other problems in the back of your book. Okay? Okay, but before we do that, let me make a few announcements. I do have your exam number 3 ready for pickup, so at the end of today's session, you should pick this up. Also, I want to remind you, the semester is almost coming to an end. Indeed, exam number 4 is barely a week from now, which is on Thursday, December 5, and that is the last official day of classes for this semester. And for the seniors, the graduating seniors, your exam is on Wednesday. Your final exam is on Wednesday, December 4. That will be in this room. In addition to that, for the graduating seniors, you also have to take exam number 4. So that means for you graduating seniors, there is a lot of work for you to do in the next week or so. Okay, finally, since we are going to be discussing infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance spectroscopy, most of the data that you need to solve problems in this area, most of them you will find them in your textbook. So what I'm going to do now, I am going to give you the pages that I want you to copy, and make sure you bring those copies to class. Anytime we want to take a quiz or exam, you could use the data on those pages. And the pages are 439, 441, 474, 475, and 465. Okay. Okay. So at this point, let us start with the quiz question that you guys have just taken. Let's begin to go over those. Okay, Erin, can you read this for us?
This mass spectral data, NC equals 182, 105, 77, belongs to a compound that only has three options.
Okay.
Oh, A, one benzene ring, one carbonyl, and a cyclohexyl benzene rings in a methyl group, C, 2 benzene rings in a carbonyl group, D, 2 cyclohexyl rings in one carbonyl.
Okay, thank you. Does anybody have an answer for this? Yes. Olive? C. So you said C. Yeah. Okay, so you have 2 benzene rings and a carbonyl. I mean, why are you guys laughing? So you have 2 benzene rings. Okay, let's try that. 2 benzene rings. That's a benzene ring. And 1 carbonyl. Okay. Okay, let's see whether this is correct. Now, what do we have here? We have the mass spectral data, M over Z. The molecular ion is at M over Z 182. What does that tell you? Molecular ion at M over Z 182. What does it tell you? That is the molecular weight of the compound, right? Very good. In other words, whatever you do must fit into 182. Okay. So that is the molecular weight. We also tell you that this molecule also have fragment ions at M over Z 105 and M over Z 77. Okay? Now, when you deal with this kind of problem, you look for the most obvious information. The M over Z 177, what does that tell you? You must have a benzene fragment in this molecule. Okay, very good. Okay, so if that is the case, let us see what you're giving us here. You have 2 benzene rings and a carbonyl. Okay, if you have benzene, let us look at this. If you take benzene by itself, the molecular weight of benzene is 78 atomic mass unit, right? Now, if you remove 1 hydrogen from here, from benzene, and you replace with some group, let's say we have some kind of group here, we remove hydrogen here, replace with R, this fragment here now becomes 77, right? Okay, very good. So now, what do we have? We have a fragment here at 77, this part of the molecule 77, another benzene fragment at 77, and then we have the carbonyl. So in mass spectrometry, what you do, you put all the pieces together, because what the mass spectrometer does is to break the molecule into pieces, and then it is your job to put them together. It's almost like a jigsaw puzzle. Okay, so now we have 77 plus 77 plus 28. What does that give us? 182. So that could be correct. There's nothing wrong with that, right? So this is a good candidate, right? So this could very well be correct because it does fit it does give you the molecular weight that you're looking for. Okay. Now, if you then look for the fragments, okay, this 77 here, that fragment will be this. That's M over Z 77, right? And M over Z 104, 105, right there. Carbonyl plus benzene, that's 105. And it fits into everything you have here. Okay? So I would say that the C is correct. But let us check the other answers. C would be the correct answer the way we have the data right here. So you have 105, 77 plus another 77, and that gives a molecular ion at 182. Okay, so let us see here. So we all agree that C is probably correct. Let us rule out the rest of them. Okay, A, benzene ring, carbonyl, and cyclohexyl. Okay, so we have this. Carbonyl and cyclohexyl. Okay, that's cyclohexyl. Let me do that better than that. Okay, so that's cyclohexyl. If you look at this fragment here, this here would be 77. Okay, by the way, when you do mass spectrometry, make sure you have your calculator ready, because that's what you do. You keep adding the numbers. Okay? Okay, of course, this here is 105. But the problem now is, this fragment here, if you add 6 carbon atoms, and 11 hydrogen, that is 1, 2, 3, 4, 5, 6 carbon atoms. Hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, this here gives you 83. Right? So therefore, what do you have? You have this fragment is 83. So if we add those together, 83, 77 plus 28 for carbonyl. If you do that, what does that give you? I believe that should be 188. So that doesn't fit. So therefore, we'll say this is not the correct. This is out. Okay. You could do the same thing for B. To do the same thing for B, 2 benzene rings and a methyl. That doesn't work. And a methyl. Okay? If you do that, this fragment is 77. Okay? And this fragment here, this part of this here, this would be 76. And of course, the methyl is 15. If you add that together, what do we get? 77, 76, and 15. What do we get? That's our 8. Okay, that's our 168. So that doesn't work. Okay? So that's the way you do this. You rule out all of the other possibilities, and you find out that the answer is actually C. Okay? So we could continue to D. I will leave that for you to determine. Okay. Let's go to the next one. Okay. Shante, can you read it for us?
This mass spectral data MP120 plus 105 27 43 was on to a compound that only has
Continue.
a carbonyl ethyl group and benzene ring, a carbonyl propyl group and benzene ring, a benzene ring and 2 methyl groups, a benzene ring and an isopropyl group.
Okay, thank you. Now, what will be the answer to this? Okay, what do we have here? We have the mass spectral data, M over Z. 120 is the molecular ion, right? So what does that tell you? Molecular weight of this compound is 120, atomic mass unit, okay? Then you have ions at 105, 77, and 43, okay? So, the choices you have a carbonyl, ethyl group, and benzene. Okay, which will be the answer here? D, you said? D? Okay, so you say this one here, let's see. a benzene ring, and an isopropyl. Okay, let us see. Will that work? No, it might work. You don't laugh yet. Benzene. And isopropyl. Okay. If you look at this fragment here, that's 77, right? And this fragment here, that's 43. Okay? If we add 43 plus 77, what do we get? We get 120. So that will work. Okay? That will work. Now, if we ask you to account for the ions, so the chances are D is correct. Okay, so now we know what 43 is, which is this here. We know what 77 is, which is this benzene fragment. About 105. What is 105? 105 will be if we lose a metal. So this is 105. The rest of the molecule will be 105. If you lose this metal here, 15 minus 120 minus 15, that is 105. Okay? So you can see here how we can use mass spectrometry to determine the structure of an unknown compound. Now, supposing we tell you that this compound here has an IR. Supposing we tell you this compound has an IR absorption at 1700 wave number. Okay? Supposing we say that. And everything else is the same. Okay? The molecular ion is 120. You have fragment ion at 105. You have another fragment ion at 77. And another fragment ion at 43. Okay, now the difference now, we say this molecule also has an infrared absorption at 1700 wave number. So what would that be? Anybody? That's an idea. Where do we start? Start with the most obvious, right? Start with benzene, right? Is that what you said? Okay. Let's just start with benzene. Okay, the first question I would also then ask you, what does this information tell you? This absorption, IR absorption at 1700 wave number. What does it tell you?
It absorbs at that frequency. It absorbs
yeah, but what does it gives? It tells you that you have a particular functional group. What kind of functional group is that? What is it?
C double bond carbonyl.
C double bond O. Yes, very good, very good. Carbonyl group. So what this tells you is that this molecule has a carbonyl group. Okay? So once it tells you that, then you are limited by your choices here. For example, you know you have a benzene ring, you have carbonyl, right? Then what is missing here? What do you need to complete the molecule? Because you have 77, the benzene, this here is 28, the carbonyl is 28, and so that is 105, and all you have left is a metal, so that's got to be a metal here. So you can see how you could use this mass spectrometry to actually determine the structure of an unknown compound. Hmm?
So, what's the answer?
Huh?
What's the answer?
Which one?
Which one is the answer?
The answer is D.
Oh, okay.
The answer is D. Okay? Or you want us to go through the other choices? No. But the answer here is D, at your own leisure, try to go through the rest of them. You find that they will not fit. Okay? Now, what other possibility can we have here? What other possibility can we have? Supposing we have this. Okay? Okay, let's call this molecule A and molecule B. Okay, with molecule A, will it be consistent with this mass spectral data? If we didn't tell you anything, okay, if I just gave you this here, and I say, give me the structure, if I did not give you this here, I did not give you these choices here. If I say, only give you the mass spectral data, and I say, give me the structure of this unknown, okay, will A be consistent with that structure or with the data? This A, why not? Why? Right? So if you look at this, molecular ion for this will be at m/z 120. Okay, if you add this, because this part of the molecule here, this fragment is 43, and this fragment is 77. 77 plus 43, you get 120. So that is consistent also. Now, supposing then, I ask you, between mass spectrometry and infrared spectroscopy, if I give you molecule A and molecule B, and I say, because this is another way we could ask you that question, and I ask you, between mass spectrometry and infrared spectroscopy, which instrument would be best to identify the structure of A or B? If I give you both of those molecules, which instrument will you use to distinguish between A and B? I give you A and B, and I've given you two instruments here, mass spec and infrared. Which instrument would be the best one to use to distinguish between A and B? Okay, yes, that's correct, but why? Exactly, because the IR will tell you you have a carbonyl group. But on the other hand, the mass spec will simply give you the molecular weight. And they all have the same molecular weight. They are all isomers. In this case, they are all constitutional isomers. So it is very difficult to use mass spectrometry to distinguish between constitutional isomers. Okay? So keep that in mind. So in this case, what you will need to use will be the infrared spectroscopy, because that will tell you that you do have a carbonyl functional group in one of the molecules. Okay, let us go to the next one. Okay, this is a big one. Okay. Okay, Nolan, can you read this for us? 3. Okay, okay, thank you. Okay, so what we need to do here, say what peaks would you expect in proton NMR spectrum of bromocyclopropane? Okay, before we go to this, let me give you a little bit of background information, because I know most of you watch the webcast for chapter 12, and not too many of you watch the webcast for chapter 13. I know that. Okay, so let me give you a little bit of help with chapter 13 here, okay? Okay, let us start by saying, let us look at equivalent and non-equivalent hydrogens in the case of nuclear magnetic resonance spectroscopy. We refer to this as proton because we are essentially looking at the nuclei of atoms when we deal with nuclear magnetic resonance spectroscopy. Okay, equivalent and non-equivalent hydrogens and carbons in organic molecules. Okay. If I start with this here, let's start with the very simple molecule. Methane, right? You have 4 hydrogens in methane. Okay, if I decide to perform this chlorination, I replace any one of those hydrogens, I get chloromethane, no matter which one I replace, right? So therefore, we say all of these hydrogens are equivalent. They are chemically equivalent. Okay, supposing I do the same thing with ethane, I replace any one of the 6 hydrogen in ethane with chlorine, 1 chlorine atom. What do I get? I get chloroethane. No matter which one I replace, I get the same product. So therefore, we say all of these hydrogens here, all of these 6 hydrogens in ethane are chemically equivalent. Okay? Supposing I go to a more complex molecule. Look at all of the hydrogens, all the CH2 groups in cyclopentane. All of those hydrogens here, I do the same reaction, chlorination. No matter which of the hydrogen I replace, what do I get? I get chlorocyclopentane, right? So therefore, I say all of these 12 hydrogens in cyclopentane are equivalent. Okay? Now, supposing now I do this. I now place a functional group on that carbon. I then ask you, how many sets of equivalent hydrogen do you have in this molecule? How many sets of equivalent hydrogen do we have in this molecule? Let's call this molecule. Well, this is cyclopentanone. Let us call it A. Okay? How many sets of equivalent hydrogen do we have in this molecule? How many? 2. Okay, let us see. We say this here, this, and this are equivalent, right? If I replace any one of them with chlorine, I get the same product. The same thing, this and this are equivalent. Okay? Now you get the idea. So this molecule has 2 sets of non-equivalent hydrogens. Okay. Very good. The same thing applies to carbon. I will ask you the same question. Okay, you look at cyclopentane. How many sets of equivalent carbon do you have in this molecule? cyclopentane is 1. Okay? It's 1. No matter what, you react any one of those hydrogen attached to any one of the carbon with chlorine, you get the same product. Now, supposing I ask you the same question here. How many sets of equivalent carbon do you have in this molecule, molecule A? How many? How many sets of equivalent carbon do you have? How many? Okay, what about this one? This is 1. This here 2, right? Both of these are equivalent. So that's 2 sets right there. And if we say 3 and 3, so with regard to carbon, you have 3 sets of carbon that are equivalent in this molecule. But with regard to hydrogen or protons, you only have 2 sets of protons that are equivalent. Okay? Now, let us do another complex molecule. Supposing we have this. Okay, let us look at this molecule here. Let us call the molecule B. How many sets of equivalent hydrogen or protons do we have in this molecule B? Okay, let me help you out here. This is 1 set right here. This 3 hydrogen on this carbon, that's 1 set. So we say 1, right? These 2 hydrogen on this carbon, that's another set. So that is 2. This hydrogen by itself here, that's another set. That is 3. Now, this is the hydrogen on this metal and the hydrogen on this other metal, they are all equivalent. Okay? So now, we say 4, 4. So therefore, with regard to hydrogen, we have 4 sets of equivalent hydrogen on this molecule B. You follow that? That is very important going forward to the NMR spectroscopy. Okay? Now, supposing I ask you, how many sets of carbon do we have in this molecule B? How many? For carbon, let us use the green pen. Okay, this will be 1 set. 1. Another 1. 2. Another 1. 3. 4. And here, both these carbon here are equivalent. So that would be 5 for carbon. So with regard to carbon, you take a look at this molecule here, you have 4 sets of equivalent carbon. Okay, now having said that, now let us now get to the NMR spectroscopy. What information do you get? Nuclear magnetic resonance spectroscopy. Okay, I know some of you did read the video before you came in here, so we are not going back all the way back to the fundamental theory. But when it comes to nuclear magnetic resonance spectroscopy, there are 4 basic information that you obtain that will allow you to determine the structure of an unknown compound. And those 4 basic information are chemical shift, two, absorption signals, three, what we call multiplicity, which we refer to sometimes as spin coupling. spin splitting, okay, for integration. Okay? Now, what does the chemical shift tell you? The chemical shift what it does, gives you information about the electronic environment of a given set of hydrogens or carbon, of a given set of hydrogen or carbon. Okay? Now, what do you mean by that? Come back to that. Supposing you have this. Still on chemical shift. Supposing we have this molecule here. The chemical shift for each one of these hydrogen here, focusing on hydrogen now, or proton, will be different. Each hydrogen in an organic molecule has a unique chemical shift because they are in a different electronic environment. Now, if you take a look at this carbon here, it's attached to oxygen. Okay, because this carbon is attached to this oxygen, all of this hydrogen here, okay, all of this hydrogen here will have a chemical shift somewhere between 2.5 to about 4 parts per million. Okay, that you remember the table that I told you that you could make copies of those pages in your book? This is the kind of information you get from those pages. So what the chemical shift will tell you is that the hydrogen that is giving this signal is next to some electron withdrawing group. Okay? It's next to some electron withdrawing group. So that gives you that is what we mean by it gives you information about the electronic environment. So what does that tell us? For example, the chemical shift for this could very well be about 3.7 parts per million for this hydrogen here. Whereas the chemical shift for this, because these hydrogen are further away from oxygen, would be somewhere about 1.2 parts per million. Okay? So the greater the chemical shift, that tells you some electron withdrawing group like oxygen, nitrogen, bromine are not too far from those set of hydrogens. Now, then look at this here. On this carbon here, these 3 hydrogens on this carbon here, we will say the chemical shift is about 2.2 parts per million. And that is typical of a methyl group that is attached to carbonyl. That is typical of a methyl group that is attached to carbonyl. So therefore, the chemical shift tells you, gives you information about the electronic environment. The greater the chemical shift, the closer the set of hydrogen will be to electron withdrawing group. Okay? Now, so that is the chemical shift. Now, with regard to signal, remember we told you the signal. So the absorption signal, right? What the absorption signal gives you the absorption signal tells you the number of different sets of equivalent hydrogen or carbon that are present in the molecule. Okay, it gives you number of different sets of hydrogen or carbons in the molecule. Okay, so we go back to here. So if we look at this molecule here, with regard to the proton NMR spectrum, what we call the PNMR, proton NMR spectrum, how many signals, how many proton NMR signals do you think we are going to get from this molecule? Let us call this molecule C at this point. How many proton NMR signals do you think we are going to get from this molecule? How many? How many? Keep in mind the absorption signal tells you the number of different sets of hydrogen that are present. So the question is, how many different sets of hydrogens are present in this molecule? Exactly, three. Okay? So therefore, the absorption signal for this will give you, you are going to get 3 absorption signals from this molecule because you have 3 sets of equivalent hydrogen. Okay? So this will be one set. This is another set. This is another set. So therefore, I expect to get 3 sets of signal from the proton NMR spectrum of this molecule. Okay, very good. So now the other set of information, we say multiplicity. What does the multiplicity tell us? This gives us the number of hydrogens, that are on adjacent carbon atoms. That are on adjacent, that is next carbon atom, atoms. Okay? Okay, so let us go back to that molecule we are looking at again. Before we go further into this, as a result of this, what we call the spin multiplicity or spin coupling, multiplicity or spin coupling or splitting, we have what we call N+1 rule. N+1 rule. This is very important. The N is the number where N equals to number of hydrogens on the next carbon atom or on the adjacent carbon atom. On the adjacent carbon atom. Okay, so the N+1 rule says if this carbon atom here, this here, you have 2 hydrogens here. Okay, how many hydrogens on the next carbon atom? How many hydrogens? With regard to these 2 hydrogens? Okay. Okay. This hydrogen will be seeing how many hydrogens? Okay, seeing will be seeing 3. It's almost as though you are looking at your neighbor. Okay? Okay, so these 2 hydrogen here, they will be looking at these 3 hydrogen. And these 3 hydrogen here, they will be looking at these 2 hydrogen. So they are on next to each other. Okay? So therefore, the n+1 rule says the signal for this hydrogen here will be split into n+1 peaks. Okay? Signal for a given set of hydrogens will be split. That is the n+1 rule. Signal for a given set of hydrogen will be split into n+1 peaks. Okay? Where n is the number of hydrogen, where n equals to number of hydrogen on the next carbon atom, or adjacent carbon atom. Okay? Okay, so let us use that, apply that rule now. So I will say, what will be the multiplicity of the signal for this set of hydrogen here? Okay, because it is this set of hydrogen will be seeing 2 hydrogen, so therefore the signal for this will be split into 3. So you have this here. So we therefore say this will be a triplet. We call this will be a triplet. Okay? And then we come back to this. About the signal for these 2 hydrogens here, these 2 sets of hydrogen, what would they be split into? Exactly, quartet, because they are seeing 3 hydrogens. So therefore, this will be split into a quartet, and the splitting pattern will look like this. At this point, you don't need to worry about this splitting pattern. This will be a quartet. So if I see in the proton NMR data, I see a quartet and a triplet. What does that tell me? Tell me I have an SE group. Okay, you have a CH3 next to a CH2. But you begin to see how powerful the proton NMR data is. Okay, now, we then come to this set of hydrogen here. We come to this set of hydrogen here. What will be the multiplicity of this set of hydrogen, these 3 hydrogen here? There is no hydrogen on this carbon. So, n is 0. 0 plus 1 is what? Singlet, exactly. So this will be a singlet. So this will be a singlet. Okay? So you begin to see we could actually use this to begin to construct the structure of an unknown molecule. Okay? Finally, the last set of information before we go to our problems in the quiz. Now I see you now have enough information to do that. Is the integration. told you about the integration. What this does is just to give you the number of hydrogens for the integration. This integration will give you the number of hydrogens that are responsible for each signal. What integration gives you is number of hydrogens or protons that are responsible for each signal. Okay? So right now I believe I've given you enough information to solve all of the problems in the quiz. Let us go back to the quiz question. Okay. Okay, Lillian, can you read this for us? Continue. Okay, thank you. Okay, so now what do we have? We have bromocyclopropane. You say, what peaks would you expect in a proton NMR spectrum of bromocyclopropane? Let us draw the structure. Okay, bromocyclopropane. What peak would you expect? Let me ask you first. How many different types of hydrogen do you have in this molecule? 2. Very good. So you have this here. And then you have this. This here and this here will be equivalent, right? So how many do you have here? Let me put 2 there. Let's see. So that how many hydrogen do you have in that set? This is one set. Okay, 2 are the same. How many hydrogen do you have in the set number 2? How many? Is it 2? 4. 4. Okay. So therefore, the question is, what will be the multiplicity pattern of this molecule? Will it be a doublet and 2 triplets? Will it be a doublet and a septet? Septet means it is seeing 6. Septet means that it is seeing 6. So 6 plus 1 is 7. That's what that means. Quintet means that it is seeing 4. 4 plus 1 is 5. That is quintet. So in other words, it is seeing 4. Sorry. So what quintet means, it is seeing 4. And that is why it is a quintet, because the n plus 1 rule, whatever it is seeing, plus 1. Okay? Triplet, of course, means that it is seeing 2 plus 1, right? Seeing 2. Here I say a doublet and, okay, so which will it be? Anybody has an idea? Which one? C? Okay. Yes. How many people agree with C? Yeah, that is correct. Okay, but no, but see, no, see, let me explain to you. See, the correct answer is C. Okay, so it's a doublet and a quintet. If you take a look at this here, this hydrogen here, how many hydrogens will this hydrogen see? How many? This here. It is seeing these 2 right here, right? This hydrogen here is seeing this here. So it's seeing a total of 4. And that gives you a quintet, according to the n plus 1 rule, right? And about this equivalent hydrogen, what are they seeing? They're only seeing one. And that would be what? According to the M+1 rule? A doublet.
So you can only add pairs of equivalent hydrogen?
Yes, yes. I mean, whatever it is seeing is what you have to, is what the multiplicity will tell you. Okay? So anyway, so therefore, the answer for this will be C. The answer for this is C. Okay? Okay? Everybody agree? Okay. Let us go to the next one. Okay. 4. Okay. First, can you read it first? Yes. Yeah.
How many sets of equivalent protons does 2 represent?
Okay, thank you. Okay, go ahead.
A6, B5, C3, C4.
Okay, very good. So in this question here, we are asking how many sets of equivalent protons does 2-methyl butane contain? We need to know the structure of 2-methyl butane. Okay. How many sets of equivalent hydrogen does it have? Anybody? Okay, let us start. Okay, will this be one set? Let me put one here, right? About this? 2. About this? 3. About this metal? Are they equivalent? Yeah, they are equivalent. Okay, so this would be 4. You only have 4 sets of equivalent hydrogen. Right? So therefore, the answer to this is D. You see how easy this is? Okay? Okay, so let us do the last one before we leave. And then maybe a couple more problems. Yes. Huh? I know, but the one I gave you, I told you not to do. Okay. Okay. Ahmed, okay, can you read it for us?
Okay. Propose the structure for the proton NMR spectrum below and assign hydrogen to the signals. Molecular formula C5H10O2, IR at 1735 in percent.
Okay, very good, and thank you. Okay, so what do we have here? What they've given us now, they have given us the proton NMR spectrum of this compound with a formula. The formula is C5H10 and 2 oxygen. Presumably, this formula could have been obtained from mass spectrometry. That's what mass spectrometry will give you. It will give you the formula or the molecular weight. Okay. They also tell us that this molecule has an IR absorption at 1735. Okay. If you look into your IR data sheet, whenever you see a peak at absorption at 1735, you say, might be most likely it will be an ester. Okay, that's the carbonyl of an ester. Okay, so say most likely it will be a carbonyl of an ester. And what does an ester look like? Must be this here. Okay, so you must have this functionality in this molecule here, which only contains 5 carbon atoms anyway. Okay, so now once you get this kind of data, the spectrum, what I want you to do is this. Write down the data in a tabular form. Write down the data in a tabular format. Okay, so let us do that. we have a peak, a chemical shift at 1.2. Look at this here. By the way, if you look at this signal here is the same as this. All they've done is just to expand the signal so we can see it. So that's a doublet. Okay? So I will start off by write everything out in a tabular form. 1.2 parts per million parts per million, and then the multiplicity is doublet. Okay, I put a D, and then in terms of the number of hydrogens, I will tell you now. I will save you some trouble. I will say this here. This contains 6 hydrogens. This peak here is 3 hydrogen, and this peak here is 1 hydrogen. Okay? If you can see this is what we call the integration line. We could actually use that to determine this line you see here. That's what we use to determine the number of hydrogen. But in this case, normally we will measure it using a ruler, but I will save you all the trouble. Whenever you have problem of this nature, I will tell you the number of hydrogens. Okay? Very often, most of the more current instruments that we use in the lab, they actually do the integration for you and give you the numbers also. So anyway, so this is 6 hydrogen here, 3 hydrogen here, and 1 hydrogen. Okay, so now let us look at this peak. The peak at 2.0. The peak at 2.0 parts per million. Okay, that's a singlet right here. You notice there is no expansion on that peak. So that is a singlet. And the number of hydrogen is 3. Keep in mind the number of hydrogen here is 6. And finally, this peak right here at 5.0 parts per million. Okay, let us look at the multiplicity. Let's count here. 1, 2, 3, 4, 5, 6, 7. That's a septet. Okay? Because what it is, what they've done is to expand this peak. That is what they've done here. Okay, so that's a septet. And it's 1 hydrogen. Okay, so now let us put the pieces together. Okay, just do this and then we leave. Let's put the pieces together real quick. Keep in mind the formula is C5H10 2 oxygen, right? Okay, you have septet, 1 hydrogen, and doublet, 6 hydrogen. What does that tell you? Doublet means that it is seeing 1 hydrogen. Septet means that 1 hydrogen is seeing 6 hydrogen. So therefore, you must have this. You must have an isopropyl group. Okay? And then, they already told us that we have an ester. And if you look at the chemical shift of this hydrogen, it must be next to oxygen at 5. Okay, so I have this. Okay, they told us we have an ester, carbonyl of an ester, right? How many more carbon do we have to go? Now, we have explained this here. We explained this peak. Those would be these 2 here. We've also explained this one here. That would be this one here. So the only thing we need to explain is these 3 hydrogens, singlet, 2 parts per million. Okay? If you look at this structure that we've given you here is consistent with this formula. It is also an ester. So anyway, this is the kind of thing that you have to do when you use the data from all of these 3 instrumentation to determine the structure of an unknown. So when we come back, after your Thanksgiving. Enjoy your Thanksgiving. When we come back, we are going to continue. By the way, if you have time, if you want to squeeze in a little bit of time, please watch those videos or webcasts that are posted in YouTube and also in Blackboard on Chapter 13 lectures, okay, as the other lectures on Chapter 13. Yes, Lecture 2 and also another lecture that is problem solving session. Okay, please watch those before we come back on next Tuesday. So enjoy your Thanksgiving. Oh, yeah, just a minute. Okay, let me give you back your exam. Last year.